The second way to visualize and therefore compute volumes of revolution is using so-called cylindrical shells. So let's just see what that actually means. The way that we think about shells is we're going to think of the exact same volumes as we have seen composed before. So let's take our parabola here and rotate it around. So let's think of this bowl. But in terms of disks, we were thinking of slicing this, let's say horizontally in this case, centering our disks on one of the axes, in this case the y-axis, the axis of rotation, and then adding them up. So it's again kind of like slicing the salami and seeing what the actual slices will be. When we're thinking in terms of cylindrical shells, we are literally thinking of how this volume is composed of little cylinders. This is a little harder to visualize at first and to think about. So here are some analogies. For example, a roll of toilet paper is composed of really, really thin cylinders, which are actually the paper itself, right? So each of those cylinders is wrapped around the core, and therefore the whole thing, while it looks solid, is actually a composition of a bunch of little cylinders. The other way to think about this is, for example, that's exactly how trees grow. The tree every year will acquire a cylinder shell that is forming on the outside, right? And so, for example, this is why tree rings can be used to compute how old the tree is, right? Every single year, the tree will acquire a full cylindrical shell around itself. My other favorite example here, although not actually very mathematically correct, is matryoshkas, Russian dolls, right? These guys are packed within each other, and each one of them is kind of like, I mean, it's not a very cylindrical cylinder, but you get the idea. Instead of slicing something vertically or horizontally, we're actually thinking of packing the same shape within itself. This is going to be a little more difficult to draw, but we will persevere and I'm sure we will succeed. Let's think about the shape of the parabola that we've already seen. So I'm going to take x squared plus 9. So once again, I have a parabola looking down 9 units up. So parabola that looks something like this. There we go, up at 9. And I'm going to rotate the region under the curve around the y-axis. Okay, so I'm halfway there. I've already constructed my the left-hand side of it, because again, like I would only really need to rotate one piece of it. And so let's think about how this is now this three-dimensional bowl-looking shape, and how can it possibly consist of cylinders inside. Now, again, this is going to be a little bit harder to actually really visualize and even draw, so bear with me here. I'm going to take a point on the curve right here, for example. You know what, actually, let me take it a little bit higher. There we go. And I'm going to draw the inside cylinder that corresponds to that. So again, think of this as like your tree. Let's say this is your tree trunk. So at this point in this year, what was the cylindrical wrap that the tree has acquired? So here, because we have rotated around the y-axis, I'm going to span it around the y-axis, and it's going to span the entire height of my tree, right? So my tree acquired more thickness that year, and that thickness spanned the entire height of the tree. So this is what's important to recognize here, is that first of all, this is once again just a typical shell, not the only shell, and you're going to get a whole bunch more of these cylinders that in the end form your entire solid. So some cylinders are going to be skinny and long, some are going to be short and chubby, like this guy right here, right? So at different levels, you're going to get different looking cylinders, but this entire volume consists of these cylinders all added up together. Now, the reason that it's called cylindrical shells is because, of course, each one of them, again, just like in the tree, will have a thickness to it, right? So it's kind of like a can, like if you stack cans within each other, right? Each of them has really, really thin walls, but they're non-zero, non-trivial walls, right? So here, let's again, just like before, we're going to draw out our typical shell. And our typical shell in this case will allow us to just simply label what we have. So here's my cylindrical shell. And again, it has a little bit of thickness to it. Not much, but just a little bit. So what do we have in terms of what is the volume of such a typical cylindrical shell? Volume of a cylindrical shell. So notice that it's called a cylindrical shell because they will always be cylinders. And the volume of such a thing is 2 pi r times the height times the width. Okay, so 2 pi r you might recognize as the length of the circumference. So it is the length of the circumference times the height of the cylinder times the thickness of the actual shell. What is it in our case? How can we compute it here? So let's start with this thickness here, because remember in the disk method, the thickness made us recognize whether we're going to be working in terms of x or in terms of y. So here, in my current example, the thickness is this guy right here. It's going to have to be very small, so it's going to be dx or dy. And in this case, it spans along the x-axis. So we're going to label it with the dx. So this thickness here, dx. This thickness here, the width, is going to be dx. This already allows us to recognize what is the main variable we're going to be working with. But what about the rest? So the radius and the height is something that I'm interested in, right? So the radius is going to be this guy here, and the height, of course, is exactly what we think of the height is right here. Looking at where this cylinder sits in our volume, if I have this as the point on my graph, which is always a good sort of starting point or your base to start drawing the cylindrical shell from, I can see that the radius is going to correspond to this distance, which really is just the x coordinate of this chosen point. So really just any x. If you give me some x anywhere on this particular region from 0 to whenever I have to go, from 0 to 3 in this case, right? If you give me any x here, I'll be able to find the corresponding point on the curve and construct the cylinder whose radius is going to be exactly the x that I started with. So x gives us the radius. What gives us the height? Well, notice here that all I have to do is take this x value and plug it into my function in order to find that point on the curve that will in fact give me the height. So the height of my cylinder here is my y value, or in our case, because we have a function itself, is x minus x squared plus 9. Excellent. Once I have this, I know that I'm going to do something very similar to what I've done with disks. This is the volume of one cylindrical shell. Now I simply have to add all of these cylindrical shells that compose my tree all together. So the total volume is going to be simply the integral of all of these shells added together. So it's going to be the integral, and then I plug in the volume of a typical shell, but with all of the information already imported into my integral here. So I'm going to have 2 pi times the radius, which is x, times the height, which is minus x squared plus 9, times the thickness, which is dx. Okay, so notice again, let me label this here. This is the radius, this is the height, this is the width of my cylindrical shell. And now, as with disks, I have to think of, well, I have my integral set up in terms of x, so I need to think of the smallest and the largest that x can be. So notice that here, don't get misled. This x corresponds to the radius, so I need to think of what is the smallest possible radius of such a cylindrical shell, and it's not going to be minus 3, it's going to be 0. It's going to be the cylindrical shell that corresponds basically to this straight line. So I'm going to go from 0 here. And what is the largest possible radius of my cylindrical shell? What's the biggest possible x I'm going to get? And notice that it's going to go from 0 to 3, right? My biggest cylindrical shell is actually going to be this one at the very, very end. So this goes back to remembering that only one side of the parabola is enough in order to produce the full rotation from 0 to 3. Okay, so again, I know that the cylindrical shells are harder to internalize and therefore might require a little bit more looking at and a little bit more playing around with, but we will do a few more examples to see how this works. So this is my next region. This is the y equals e to the negative x, and I'm given it on the interval from 0 to 3. I would like to revolve the region under the curve around the x-axis and then find the volume of the resulting solid. So notice here that I've already switched axes. In the previous example, we rotated around y. Now we're going to be rotating around x. Let's see how that will be different. So first of all, I'm going to draw out my curve, and I have that it's e to the negative x, so it's an exponential function, decreasing, decaying exponential function, something like this, right? And I'm interested only up until 3, so let's say this is my point 3. I notice that if I plug in 0 into here, e to the negative 0 is 1, so I know that this is up at 1. Excellent. Now I'm going to rotate this around x-axis, so I have to take this production with me and rotate down around the x-axis. So the first thing I can do is just flip this picture, produce the mirror image of it. This is not bad, close enough to actually be fairly symmetric. And then draw in maybe just like a few lines to make it look three-dimensional here, right? So there we go. With cylindrical, if we're using cylindrical shells, be particularly careful not to really add too much information onto your sketch, because the cylinder itself will contain quite a few lines and curves, so you don't want to make your sketch too busy. Okay, so how are we going to think of this as consisting of cylinders? Well, the same way as we did before. It's just now that your tree trunk is actually the x-axis. So your tree is growing in this direction. So if you want to like rotate your head a little bit, this is the tree trunk that you're working with. So this is what the cylinders have to span around. Okay, so this is going to be the core of your cylinders, the core of your tree, and all the cylinders have to be built along this way. So then the first thing to do, just like I did last time, is actually pick a point. Pick a point anywhere on your function. Think about what the core is, and then draw the cylinder that goes through this point around this particular core. So in this case, I'm going to get something that looks like this, goes around, and then all the way the entire height of your tree and around this way. Now also remember that once you draw your cylinder, you have to give it non-trivial thickness, because the tree did acquire non-trivial amount of actual wood on the way to growing. And here we go. So the first thing after this to note is that your thickness is what determines what variable you're going to be working with. So my thickness is here, it spans along, or it is parallel to the y-axis, which means that my thickness here is going to be denoted dy. And then the rest of it will therefore have to be set up in terms of y. So this means that the integral is going to be in terms of y. This now means too that I can't work with the function as I have it written down. I'm going to have to rework it so that my function is in terms of y, not in terms of x. So let's do that first. So I have e to the negative x, which means that in order for me to isolate x, I'm going to take ln of both sides. So what I'm going to have here is ln of y is equal to minus x, which means that x is equal to minus ln of y. And this is going to be the exact same function, but rewritten for the other variable. And now we go through the exact same thing as we've done before, where we actually think about the volume of a typical cylindrical shell and then put it together in the integral. I'm going to write down the integral right away, but I'm going to first of all keep the volume of a typical cylindrical shell in it. So 2 pi r h w. And let's see if we can fill out the radius, the height, and the width. So the width or the thickness I already know to be dy here. This again is what dictates my main variable of the integral. And now let's think of what my radius and my height are going to be. In different scenarios, it doesn't really matter which one you start with. Sometimes one is easier than the other to picture. And I think it really also depends on the person and how your visualization actually works. So let's look at the cylinder once again. This is my cylinder right here. If I pick a point on the curve, then that point determines the height of my cylinder and also the radius of it. But you're going to have to think of which one is which. So for example, let's concentrate on the radius first. The radius is this distance right here. This distance right here, of course, is the y-coordinate of this particular point. And I know that my entire integral has to be in terms of y, so that's all I'm going to use. My radius is the y-coordinate of any given point. The height of my cylinder, this guy, is of course the x-coordinate of this point itself, and the x-coordinate is given to me as the function of y here. So the x-coordinate I can simply plug in as negative ln of y. Okay, so again, this is going to take quite a few times or quite a few examples to really see. The height is the x-coordinate, but my integral is in terms of y, so I'm going to write it in terms of y, whereas the radius here is the y-coordinate, and because my integral is in terms of y, I'm just going to keep it as y. Okay. It might also help to, for the first couple of times, to maybe produce the exact same sketch, but also have another cylinder present. Again, I strongly recommend not drawing more than one cylinder on one sketch. So I would copy this sketch over and maybe think of the cylinder in sort of later or earlier, whichever way you're thinking of it, days of this tree that's going to be wider and shorter, or another cylinder that's back here that's going to be longer but thinner. Okay, and then the next step, of course, is to determine what your integral goes to and from. My integral is in terms of y, so I'm going to have to think of the smallest y value I can have and the biggest y value I can have. The smallest y value, so y corresponds to the radius of the cylinder, right? What is the smallest y value and the biggest y value? Well, the smallest y value is going to be the one that happens here. This is the smallest radius for any of the cylinder I'm going to see along the way. This is going to be the cylinder like right here, right? The x for it is 3, but I'm not interested in the x, I'm interested in the y, so you got to be careful. If x is 3, then what is y? If x is 3 here, then y is going to be e to the negative 3. Okay, and what is the widest, the biggest radius of the cylinder I can obtain? Well, it's going to be this guy right here, right? So that's going to happen when x is 0, really, x is 0 right here, which is going to happen when y is equal to 1. So I'm going to have 1 here. So if I want to rewrite it fully in terms of all the information that I have 2 pi and then radius, which is y, and then height, which is minus ln of y, and then the thickness, which is dy. Okay? Again, I'm not actually so interested in evaluating these integrals because I'm not interested at this point in practicing the actual techniques of integration. I'm more interested in the setup of these integrals, but please feel free to actually carry through the calculations and figure out what this volume is. In the meantime, let's take a look at a familiar example we've already seen, the sphere example. So in this case, I'm going to think about rotating this half a circle around the y-axis. And I'm going to notice that I actually only have to do this on the half circle that's drawn and then multiply it by 2 for the bottom of doing the exact same thing, right? So I'm going to keep that in mind, but in the meantime, I'm simply going to work with the top of the circle and the top of the sphere. Then let's think about what is the typical cylindrical shell going to look like? Again, what I need to do is first plant a point on my graph, and remember what is the core of my tree. So if I am rotating around the x-axis, then the core of my tree, or sorry, the y-axis, then the core of my tree is the y-axis. So that means that my cylinder has to wrap around that axis and be built along that axis. Here is my cylinder. So let's draw in the typical cylinder this way so that we can label it with all kinds of useful things. So there it is in the back, coming down all the way around. And one more thing that I have to introduce to the cylinder is the thickness of it. There we go. So what do I have here? Let's build the volume of the sphere now. So once again, I am remembering the fact that I'm going to actually only take the top half of the sphere, and therefore to get the full volume of sphere, I'm going to have to multiply what I get from here by 2 because I'm not accounting for the bottom. And then I'm going to have the cylindrical shell set up for this. So I have 2 pi r h w. Okay, and let's start filling this information in. So what have I got here? First of all, I can determine the width of my cylinder. It's this guy right here. It spans, it's parallel to the x-axis, which means that the width is going to have to be dx. And that means that my entire integral is going to have to be in terms of dx. This is now going to be my variable of choice. Now for this cylinder, I have to determine the radius and the height. So let's go back to the picture. If this is the point that I planted on my function, then the radius is this length right here, which of course is the x-coordinate of my point that I chose. Because my integral is already in terms of x, my radius then needs to simply be x. If I have to now think of the height, again, same point, the radius was the x-coordinate here. For the height is of course the y-coordinate of this point, which I have to express in terms of x. So remember from my previous calculations, x squared plus y squared is equal to r squared is the equation of the circle, which means that if I solve for y corresponding to the top half of a circle, I'm going to get square root of r squared minus x squared. So then this is exactly my height, r squared minus x squared all square rooted. Okay, and now again, thinking about what is it that I'm going to and from in terms of my x. My x is what my radius is. The smallest radius of any cylinder that I can build is going to be 0, correspond to the cylinder right there. And the biggest width cylinder I'm going to build is of course going to correspond to the full span of my semicircle. It's going to be this cylinder right here. So from 0 to r. Okay, so all together I get 2 integral from 0 to r 2 pi x square root r squared minus x squared dx. Okay. With the cylindrical shells, you often get integrals that look a little bit more complicated, although they don't really necessarily have to be. So here I can notice that I can take 2 pi out fully, and then you see this square root and you're thinking, oh no, trigonometric substitution. But then don't forget that you have this handy little x here, which means that this integral can actually be solved using simple substitution of u equals r squared minus x squared. I strongly encourage you to actually go through with this substitution to see how it all works out, and then come back to see the fully written out solution. Okay, so carrying through with this substitution, we found du, plugged it all back in. Notice that this x and this 2 sort of went away with the du, and I end up with a fairly simple integral that I can then take an antiderivative of, because I only have a square root of u, so I'm going to end up with u to the power 3/2 over 3/2. Notice that I actually dropped the limits of integration for now because I didn't want to recompute them for u. I'm simply going to bring back my integral to be in terms of x, and then have my limits of integration back as from 0 to r that I had previously. Now I have to plug in r in for x minus 0 in for x, and I get an already familiar 4/3 pi r cubed. Okay, so we better get the same answer because this is, we know to be the volume of the sphere. We've proven it last time, and it does come out to be the exact same. So the method does not, of course, change the answer, and you can choose which one you prefer. We will see some examples that are going to be easier done with disks and some that are easier to be done with cylindrical shells, and unless the method is specified, you're free to pick whichever one you actually use. Now let's think about how we can summarize what shells are when rotated around the y-axis and rotated around the x-axis. So on this left picture here, I of course have the rotation of this curve around the y-axis. So what do we end up with in terms of the cylindrical shell? Well, let's see. Again, the first clue to us is the thickness. The thickness of the shell here is parallel to the x-axis, which means that the thickness is going to be dx, which means that the entire integral is going to have to be in terms of dx. So what I'm going to have is 2 pi times the radius times the height times the thickness. So now let's think of what's the radius going to be if I am going to have my integral in terms of x. For this point, the radius of my cylinder is the x-coordinate of that point, and my integral is in terms of x, so I can simply leave the x. And for this point, the height of my cylinder is the y-coordinate of that point, and therefore the function value at that point times the thickness of my cylinder. And some two values, a and b. Now, if we are rotating our, let's say, half a circle around the x-axis using cylindrical shells, we're going to see something a little bit different, of course, in terms of setup. And again, we're going to start with what is the thickness of my cylindrical shell, because that will dictate the terms of my integral. The thickness here is this value. It is parallel to the y-axis, which means that this is going to be dy, which now means that the whole integral has to be in terms of y as a variable. So I'm going to have 2 pi times the radius of the cylinder times the height of the cylinder times the thickness. So let's see, if this is the point on my function, then the radius of my cylinder is this guy right here, which of course corresponds to the y coordinate of this particular point. And because my integral is in terms of y, that is what I'm going to leave. And then the height of the cylinder is this value right here, which of course corresponds to the x-coordinate of this point, which is the function value for that point y times the thickness. So notice a few things here that are going to persist whenever you use the cylindrical shells method. If you're rotating around the y-axis, that means that your cylinder uses y-axis as the core, which means that its thickness is actually in terms of x. So rotation around the y-axis will end up with the integral in terms of x. And then the other way around. If we're rotating around the x-axis, the core is going to be the x-axis, which means that the thickness is going to be in terms of y, and your entire integral is going to be in terms of y. Also notice that you can remember it sort of with the other indicator, and that is the radius. If we're rotating around the y-axis, the radius is going to be x, and that's what's going to appear here. If we're rotating around the x-axis, the radius is going to be y, and that's what's going to appear here. Next time, we're going to see the two methods side by side, but for now, please do practice with cylindrical shells. They are hard to picture, but they're a really powerful method that is very useful.